Okay, so here in this particular video, we have a velocity time graph of a particle moving in a straight line, and it wants us to find A, B, C, D, E, and F. If you need to, pause, read, otherwise keep up. Let's do part A. Part A wants us to find the average acceleration for the whole entire motion here. Okay, so to find the average acceleration function, all you have to do is set it up. A average is equal to change of velocity over change in time. I'm gonna go ahead and expand delta V into VF minus VI. That's because I need to figure out 2 points on this particular slope that I need to use. Well, here you can pick any 2 points on the slope because the way I see this graph is that this particular slope is a constant negative slope. So it's suggesting that acceleration is the same throughout the whole entire 6 seconds given in the graph here. All right, so I'm just gonna go ahead and pick two hopefully smart points. I'm gonna start with the initial value here at 0 and 3, which is right there. And then I'm going to pick the second point, which lies on the horizontal axis, which is time axis here. Again, you can pick any 2 points you want as long as you're consistent. It should work out the same, okay? All right. So because I picked the first point on the y-intercept, and then the second point is on the x-intercept for this graph because it's kind of nice, I'm just going to plug values in. Well, what's my VF at 3 seconds? That's where my point is. If I go across here, the time axis, it suggests that velocity is 0, so I want to plug in VF as 0. Well, what's my VI? The first point that I chose is at times equal to 0, so my velocity here is at 3 meters per second to start. So VI is just 3, 0 minus 3 is negative 3, and then the time interval here that I've chosen is 3 seconds. You could go from, 0 to 6 seconds if you want. I just chose to go from 0 to 3 seconds just because I see that at 3 seconds lies on the x-intercept, which suggests that velocity is 0. Okay, so again, just make sure you interpret these graphs correctly. So negative 3 over 3 is just going to be negative 1 meters per second square. So that is your average acceleration equation for this one. And it makes sense because, once again, this is a velocity time graph. The slope of a velocity time graph tells you your average acceleration. And in this case, it's negative because just by looking at it from left to right, this is a negative slope. And it goes down 1 over 1, which match the answers that I've concluded there. Okay, all right, let's do B. B wants you to find the instantaneous velocity at 4.7 seconds. Well, to find the instantaneous velocity, all you have to do is once again set up your average acceleration equation. Average acceleration is equal to VF minus VI divided by T. Well, here instantaneous velocity is the same as VF, so all you have to do is really isolate for VF by doing algebra correctly. So to get VF by itself, I need to first get rid of this delta T. So I'm just going to go ahead and multiply both sides by delta T. That tells me that A average times time is equal to VF minus VI. You notice here I don't have VF by itself yet, so to get rid of VF, I need to do the opposite operation here. So this is minus VI, so I'm just add VI to both sides. Or I like to think just this negative VI, move to the other side, and then change the sign, okay? So VF is simply A average times time plus VI. Well, this is pretty light work. I already found A in the previous part, which is negative 1 meters per second square. Well, how much time here? I want to start at 0 second and go to 4.7. So therefore my change in time here is 4.7 seconds. But what's my VI? My VI is going to be 3 because I started at 0 seconds. Once again, anytime you're given a time, it's up to you to figure out which time interval you like. Here, I started from times equal to 0 and just go all the way to 4.7 seconds because according to the graph, my initial velocity at times equal to 0 is given as a positive 3 because it's above the horizontal axis, so I know that value already, so might as well just use it. Okay, so here, negative 1 times 4.7 is negative 4.7 plus 3. That's going to give you negative 1.7 as an answer, which makes sense because on the graph here, if you look at it, 4.7 lies between 4 to 5, and if you go down to the graph, graph is right there, right? So if you go across, again, you can roughly even eyeball it. It's like negative 1.5, but if you actually do the math, it's negative 1.7, okay? Which makes sense, right? Because I know, according to the graph, 4.7 seconds goes down. It's in the negative region of the velocity if I go across, so I know my answer makes sense because it's negative something. All right, in this case, it's negative 1.7. That's that. All right, now, if you want to, though, again, as I said earlier, when you're given these type of instantaneous velocity questions, it's up to you if you want to start from 0 to go to 4.7, or I like in this one, if I were personally doing this, I would just go from 3 to 4.7. Well, why do I want to start at 3 seconds? Because as I stated earlier, at 3 seconds, if you go across here, your velocity is equal to 0, right? So I can just go ahead and set up the same function. Average velocity times time plus VI is equal to VF. Now, if I start at 3 seconds, though, it makes my job a lot easier. Well, at 3 seconds, the graph suggests that the object's velocity at that moment in time is 0. So, if I start at 3 seconds, my VI is 0, so I can just cross it out. My average acceleration already found earlier, which is -1 meters per second square. The only thing you really have to kind of be careful here is the change in time. So the change in time here would simply be 1.7 seconds because I'm starting at 3 seconds and I'm going to 4.7 seconds. So the difference there would just be 1.7 seconds, right? So make a choice, be careful with your time interval, know where you're starting, know where you're ending. So for this one, once again, I start, if you choose to go this route, I would start at 3 seconds and go to 4.7 seconds. So the change in time there would simply be 1.7 seconds. And as you can see, -1 times 1.7 is -1.7, which matches with what I derived earlier using from 0 to 4 seconds. Okay. All right. Let's go ahead and do C. C wants you to find the average velocity during the first second from 0 to 1. It's known as the first second. So the average velocity function is displacement over time. Well, in this case, you're given a velocity versus time graph, so the area beneath the graph is your displacement. You just have to know how to shade. So always start from the graph itself, the line of the graph, and then just go down to the t-axis and stop there. So here I've broken this area up into two different shapes. Once again, part C wants just the first second. So here is the first triangle. I want to find that area. Area of a triangle is just 1/2 times base times height. And here the base is just 1. The height is also just 1. So this would be from 0 to 1. And then this is 2 to 3, so which is 1 and 1. So 1/2 times 1 times 1 is just 0.5. But here I put positive because the area above the t-axis is known as positive displacement. Okay. And then the second shape, in order for me to complete this particular task, is just a rectangle. Well, to find that particular shape, it is a rectangle, so it just be base times height. Well, what's your base? Just 1 from 0 to 1. And what's your height? Is 2. Alright, it's pretty straightforward, right? All you have to do is make sure you count correctly. So if you plug this in, your base is 1, your height is 2, and if you if you do this correctly, 1 times 2 is just 2. But once again, this area is above the t-axis, right? It's above the horizontal axis, so that's a positive displacement. Displacement is a vector, so anytime it's above, it's positive, anytime it's below, it's negative. So just using basic math, this is a positive 0.5, this is a positive 2, so if you add that together, you get positive 2.5. Well, what's your time interval? The time interval here would just be 1 second because the question, or part C, says from 0 to 1 second, which is a difference of 1 second. So positive 2.5 divided by 1, which is give us positive 2.5 meters per second. That's our answer, okay? Now, if you want to, you can totally use kinematics equations, right? I'm still doing part C. Average velocity, by definition, once again, is displacement over time. Well, how do you find what the displacement is if you actually want to crank out the math using kinematics function? Well, delta x is VIT plus 1/2 AT squared. Well, what's my VI? My VI is 3. The graph said so because I'm starting at 0 second. What's my time interval? 1. What's my A? -1, because you need to find the slope of this graph, which happens to be -1 for this one. That's pretty straightforward. Well, what's your time interval here? There's just 1 second. Square that. So 3 times 1 is 3. And then this is 1 square, which is 1. 1 times -1, which is -1. And then -1 times 1/2, which is -1/2. So 3 plus -1/2 is 2.5. Okay. So as you can see, the displacement here is already matching with what we have earlier, just used by the area. So if you want to plug it back in, here I have highlighted delta x for you, which is positive 2.5. I left out the positive sign just because this is just, I'm just showing you how to apply kinematics here if you wanted to. All right, other than that, 2.5 divided by 1 is 2.5. The answer is positive, once again, because average velocity is a vector, and you need to include the sign, and it's above the t-axis, okay? All right, let's go ahead, and if you want to, you can also use a particular function, average velocity when acceleration is constant. And this function here is kind of tricky, okay? You can only use this when acceleration is constant. Well, if you look at the graph, the whole entire time, the slope of this graph stays constant, which suggests that A is a constant value. It hasn't changed. All right, so the slope of this whole entire shape here is just -1 meters per second squared because it's constant. I can use this particular function. Average velocity is VF plus VI divided by 2. Once again, you can only use this when A is one single slope, so you just have to learn how to chunk problems up if you need to. Well, What's my VF? My VF can be found by using AT plus VI. A, once again, is -1. How much time? 1 second. What's my VI? VI is 3, which is given. So -1 times 1 is just -1 plus 3, which is -1 plus 3 is +2. So if you crank this out, VF is 2, VI is 3 divided by 2. 2 plus 5, 2 plus 3 is 5. I'm getting ahead of myself here. 2 plus 3 is 5. 5 divided by 2 is 2.5. And once again, the positive sign here is there because this particular motion is moving to the right during the first second, because all these velocities are positive. Okay, that's that. Let's go ahead and do part D. Part D wants us to calculate the average velocity during the first 6 seconds from 0 to 6. So just cranking out using the same strategy here. Once again, average velocity is displacement over time. Well, how do I find displacement? Well, to find displacement, all you have to do is find the area underneath the graph, right? You just have to start from the graph, stop at the t-axis, and start from the graph and go up and stop at the t-axis. So it's important that you know how to shade correctly. So if you find this particular area of the shape is a right triangle, so this is 1/2 times base times height. Well, what's your base? Your base is 3. So if it's 1, that's 2, that's 3. Well, how tall is it? 1, 2, and 3. So it'd be 1/2 times 3 times 3. 3 times 3 is 9. 9 times a half is 4.5. There's a positive sign here because this area, once again, is above the t-axis. So my displacement is a positive quantity. It's moving to the right. Okay. Well, it wants us to go from 0 to 6. Due to symmetry, this area here is also the same. So 1/2 times base times height. However, I highlight the negative sign here for you because this area is now beneath the t-axis, right? If it's beneath, your displacement is negative. So it essentially tells you the object's moving right, and then it turn around and move leftward. Well, if you look at this, the area that we found previously is plus 4.5. The area now is negative 4.5. Well, negative 4.5 and, positive 4.5 and negative 4.5. If you add those two values together, you get 0, right? They cancel each other out. So what's your displacement? Your displacement is 0 because it's essentially telling you you started, you moved to the right, you stopped, and then you went all the way back to where you started. Well, you haven't changed position yet, right? Your displacement is 0 because you're back to exactly where you start. So your displacement delta x is 0. 0 divided by 6 seconds is just 0. So the answer here is just 0. All right. So that's that for part D. If you want to, you can also do this particular method. All right. Average velocity, once again, is displacement over time. Well, how do you find displacement using kinematics? Delta x is vi times time plus 1/2 at squared. Well, what's my vi? My vi is going to be 3. What's your t? T is going to be 6. Well, your a, once again, is already calculated in previous part A. It's -1. Your time here is 6. So if you do this correctly, 3 times 6 is 18. Well, 6 squared is 36. 36 times -1 is -36. -36 times a half is -18. So you have an 18 that's positive here, and you have a -18 which cancels out. That leaves you with 0. So it makes sense, right? So your displacement essentially is going to be 0. 0 divided by 6, once again, is 0. So you can analyze these average velocity simply by looking at the area beneath a velocity time graph, or you can crank out your kinematics. It doesn't matter. It should work out the same. All right, let's go ahead and do part E. Part E wants us to find the average speed during the first 6 seconds, right? So the difference between D and E is one says average velocity, which depends on displacement, while the other one says average speed, which depends on distance, and distance is a scalar. It doesn't matter which way you move, okay? So I'm just going to go ahead and bust it out. Average speed is distance over time. Well, how do you find distance? Distance is pretty whack. Distance essentially is a scalar. So whether you move right or left, you just need to add everything because it doesn't have a direction. So here in my work, I have a positive 4.5, but I put the absolute value around it because absolute value just means magnitude. And I want to add, right? So it went 4.5 to the right, and then it went 4.5 to the left. But because distance is a scalar, you don't really care whether it moves right or left. You just add everything. Right? You add forward, you add backward, and so on and so on. So here, 4.5 plus the absolute value of -4.5 is 4.5. So 4.5 plus 4.5 is 9. And how much time? 6 seconds, because the interval given to us here in part E is from 0 to 6. Okay, so you essentially can use the same strategy regardless of the time interval. You just have to know what to look at, right? So 4.5 plus 4.5 as stated is 9. And the time interval here is 6. 9 divided by 6 is 1.5 meters per second. Because it is average speed, it doesn't have a direction because speed is a scalar. So the answer would simply be 1.5 meters per second. Okay, that's that. Now let's do part F. Part F wants us to find which of the following position graph correspond to the velocity time graph given. Well, I'll show you how to do this quickly. So here you're given 8 graphs, right? Your job is to pick which graph represents this velocity time graph. So it's important that you understand what to look for, right? So here we go. If you look at choice A, okay. Oh, excuse me. Before I do choice A, let me just show you how to analyze this particular graph. If you look at this particular velocity graph, VI is positive because it starts at 3, and it's positive because it's above the t-axis. And then here, V is still positive because if you pick a point and you go across where it touches the y-axis, all these values are positive, right? However, A is negative because the slope of this graph is negative, and the slope of a velocity time graph tells you A. So when V is positive and A is negative, it tells you the object is slowing down, which makes sense, right? To me, the initial velocity is positive 3 because it's moving to the right, and then all of a sudden it comes to a stop at 3 seconds. And after 3 seconds, the line continues in the negative region, which suggests that velocity is now negative. So I'm just going to label everything for you. Hopefully, if you need practice, do this for yourself. Well, what is your velocity at 3? 0, because on the graph, if you go across at 3 seconds, it's 0. Well, what's your A? Your A is still negative because the whole entire time, the slope of this graph is a negative number, okay, which is -1. Well, if I now go into the negative region, well, what's my velocity here? My velocity is negative because if you pick a point here, this is like -1. If you pick a point on the dot, you go across, this is negative, I don't know, 2.8, whatever it is. The point is that when it's below the t-axis, when you give them a velocity time graph, the velocity is negative. Well, once again, the whole entire time, the slope of this graph is negative, right? Because it just keeps on going down. From left to right, this is negative slope. So what does this mean? Well, when V is negative, A is negative, it tells you that it's accelerating, it's speeding up in the negative direction. So it's getting faster going to the left. So this is important. So the first 3 seconds, the object is moving right, but it comes to a stop. And then after 3 seconds, it accelerates in the negative direction. So it moves right, slow down, and then from there, it turns around. So here in part A, here in graph A, how do I know if it matches what I'm looking for, right? Well, I can just draw a tangent line. This is an x to t graph. The tangent line of an x to t graph tells you your velocity. Well, if you look at the slope here, this slope is a negative slope, right? Watch my cursor. For graph A, if I just extend the slope that's given to me, that is a negative tangent line. Well, the tangent of an xt graph is your velocity. So this is saying it's moving in the leftward direction, but that contradicts what the graph is. The graph says that at times equal to 3, your velocity is positive 3 because it said so. But this is saying it's some negative number. So for that reason, okay, I'm just going to go ahead and cross it out. It doesn't match with what I need. All right. Okay, let's go to B. Now for part B, I'm just going to draw a tangent line. Okay, the tangent line here at the beginning is flat, which suggests that the initial velocity is 0, which already contradicts what this graph over here is telling me. At times equal to 0, this velocity time graph tells me that the object is already in motion at a rate of 3 meters per second. So for that reason, I want to cross it out. It's saying that it starts at 0, but the graph is saying it's actually moving already to begin with. So because it doesn't match up, I want to cross it out. Now let's go to C. For the same reason, I want to cross C out. If you extend this graph across the vertical axis there, right, draw a tangent line that go across the t-axis. Well, if you look at this graph here, the slope is some negative slope. Well, if it's negative slope, this is an x to t graph. It tells you that your initial velocity is a negative value, but that contradicts with the velocity time graph given. The velocity time graph given here is a positive 3, but this is saying that it's moving leftward. So for that reason, I'm just gonna go ahead and cross it out. It's saying VI is negative, which is not what's given. All right, let's go to D. D, for the same reason, I'm just gonna go ahead and draw a tangent line there. This tangent line is your velocity. So it's saying the initial velocity is negative, okay, which once again is kind of whack. Your initial velocity in the graph is positive 3, so it doesn't match. So I'm gonna cross that out. Now let's go to E. Okay, I want to draw a tangent line. The tangent line here is a positive slope because from left to right, this is a positive slope. Well, I want to go ahead and label that out. VI is positive, which could be, right? So here in the graph that's given, it's saying the initial velocity is a positive 3. Well, I just established by drawing a tangent line that this VI is positive. Well, how do I know if it matches with the shape? Well, this is a parabola, right? So therefore, the peak here, the tangent line is 0, which means it came to a stop. And all of a sudden, if I draw another tangent line to the right of the graph, this particular tangent line, this is a negative slope. So it's moving now leftward, which essentially matches with what we're given, right? So if you look at it carefully, the velocity time graph gives us that VI is positive 3 to begin with, right? and then it came to a stop at 3 seconds, which is essentially this particular peak. And then after 3 seconds, the velocity is negative because it's now moving in the negative region. Well, here's V is negative. It matches with what we're given here. So for that reason, I'm just going to highlight B. I'm going to ignore F, G, and H because it's not a select all that apply. So that is it for this particular problem. All right. I hope that helps. Stay nerdy. Don't be wired.